So today we are going to cover this wall and column form design. So wall and column form design is in the same pattern as it is the design of slabs. Okay. So for example, in the slab, you also have the sheathing. In the wall, you also have the sheathing element, okay, to for the concrete. And then those sheathings are supported by beams, which in this case are called as the studs. Okay, so these beams are called as the studs. So for example, over here, this is the stud. These are the studs. So this is the plan view, and on the left side it is the section view. So this is the studs. So studs are supporting the sheets, and then the studs were called as the joists in the case of the slabs. And the difference is that in the case of the slab, of course, we have to provide the beams. We have to support only on the one side, only on the one side. But in the case of the walls, we have to provide the support on both sides. Okay, both faces of the wall. Okay, so there will be then joists or the studs on both sides, sheets on the both sides. So the studs, which were called as the joists, are used in the walls. And then these studs are supported on further on another beam, which is, so if we take this plan view over here, so the studs are the vertical beams. Okay, studs are the vertical beams, whereas if we take these the wales, which support the studs, they are the horizontal beams in the plan. Okay, so wales have the same function as the stringers in the case of the slabs, and further, then the wales are then supported by the ties. So ties are just vertical. So the ties are those long sticks which are bolted or wedges together on the both sides. And then the elements of these find the span of the sheets. We need to find the span of the sheets. We need to find the span of the wales, studs. Okay, and we also need to find the span of the wales or the tie spacing. So these are the elements. If these spacings are fixed, then on the other hand, then we have to find the appropriate section for the wales and the studs for that purpose. So if you have gone through this example number 1, the example number 2, which is for the wall and the column form design. So for wall and column, the form design is following the same principles. So this example is on the same pattern as for the example for the slabs. So example 2. So forms are being designed for an 8-foot, that is 2.44 meter high concrete wall to be poured at a rate of 4 feet per hour or 1.219 meter per hour. Internally vibrated at a temperature of 90 degree Fahrenheit or 32 degrees centigrade. The concrete mixture will use type 1 cement without retarders and is estimated to weigh about 150 pounds per cubic feet or 2,403 kilogram per cubic meter. sheathing will be 1.2 meter by 2.4 meter sheets of 3 by 4 inch or 19 millimeter thick class 1 ply foam with the face grain perpendicular to the studs. And the studs and double wales will be I was disconnected actually. So, okay, let's start again where I was here. So I was talking about the snap ties. Snap ties are about 13.34 kilonewton capacity with the 38 millimeter wide wedges bearing on wales. And deflection must not exceed L by 360. This should be L by 360. 360 is missing from here in the printout. Determine the stud, wale, and tie spacing. So this is what these are our objectives in the design of this. We have to find the spacing because the section sizes have been given to us. So if the section sizes have been given to us, so we have to find the appropriate spacing. So this is our design problem. Or if the spacing has been given, then we have to find the section properties. Or in both cases, the design will also involve choosing the spacing and the section sizes as well. So in that case, one of the item has been given, so we can find the other one. But in some cases, in more practical situations, maybe we have to find the section sizes and the design and the tie spacing both at the same time. So in those situations, we will choose some of the section first, and then we will find the spacing for that, if that is appropriate for us. So in those sections, we can use from the available sections. So use ply form section properties and allowable stress from table 6 and lumbar section properties from table 7. So these are the two tables we have also seen before in the example for the slab. Allowable stresses for the lumbar being used for the studs and wales are as follows. So these are the allowable stresses. So we remember that we also use some of the allowable stresses in the case of the slab. So these are the allowable stresses and modulus of elasticity which can be used in this example. So can you hear this? Can you hear me and also see this screen? I just want to confirm.
Yes, we hear you. The PDF file.
Okay. So in the the solution, okay. So the solution is this, as I have said, that the solution is on the same pattern as it was for the example for the slab. So we start from determining the design load. Okay, so remember that for the design load, the formulas for the wall and column are different than for the slab. And right at the very beginning, we looked at this formula. Okay, that is the horizontal pressure which is exerted is given by the CW, CC, and so where CW was the weight coefficient, the unit weight coefficient, CC was the chemistry coefficient, and then this was the formula. So P is equal to CW 7.2 plus 785 R over T plus 18. So where CW was 1 and CC was 1. Why? Because CW depends on the unit weight of the concrete. Okay, so if you see one of the table before, so I have to go several pages before. Let me go quickly. Yeah, here. So you see that this was the formula. Okay. The first one is in the pound per square foot units. The second one is in the kilopascal unit. So this is the formula for the vertical pressure. And then remember that there were three formulas. Okay. So we will use this formula. So there is this another formula as well. So this formula is for a condition when column and wall with the vertical placement rate of less than 2.1 meter per hour and a placement height of 4.3 meter or less. So this was the situation, right? If I go back to this example, here is this. If I go back to this example, so it is said that the placement rate was 1.219 meter and the height is 2.44 meter. Okay, 2.44 meter or 1.219 meter. So if I go back to this over here, yeah. So the placement rate is less than 2.1 meter. Ours one was 1.21 meter, and the placement height is 4.3 meters. So ours is also is less than 4.3 meters. So we will use this formula. If any of these conditions is not meeting, then we will look at some other formulas. So the appropriate formula is this. So in this formula, CW and CC. So CW is the unit weight coefficient. So unit weight coefficient depends on the density of the concrete. So the density of the concrete we are using as 2403. Okay, 2403. So the density is 2403. So which is between 2243 and 2403. So for this, the weight coefficient is 1. Okay. Otherwise, if the density is less than 2243, then maybe you can use this and then other values. So here it is only 1. And CC is the chemistry coefficient. So chemistry coefficient, it is a type 1 cement. So in this, our example, we are using a type 1 cement. So without retarder. So we will be using a CC of 1. Okay. And R is the rate of vertical placement. R is the rate of vertical placement and T is the temperature. So these values we will input into this formula. Yeah. Here. Yes. So 7.2 is from the formula, 785 is also from the formula. R is the vertical rate of placement, which is 1.219 divided by temperature, which is 32 degree Fahrenheit plus 18. Okay. And then when it is calculated, that that horizontal pressure in the wall by the concrete is 26.3 kilonewton per square meter. So therefore, we will make a design based on this pressure, 26.3 kilonewton per square meter. This 26.3 kilonewton per square meter has been rounded up to 28.7 kilonewton per square meter. It is because in this example, they have calculated it to be 550 pound per square foot. So this 550 pound per square foot pressure, they rounded up to a round figure of 600 pound per square foot, although it is not required, but maybe to remain on slightly on the safer side, they have rounded it up. So corresponding to 600 pound per square foot, the pressure value is 28.7 kilonewton per square meter. So this value will be used. Okay. Then once we have determined the design load, then what we can do is we can find the stud spacing. Okay, remember that stud is the same as the joists in the beam. Okay, so these are the beams. So beam spacing. So beam spacing will be used because those beams, those vertical beams in this case, will support the sheets. And in this case, we will assume that there are 3 or more spans. So we assume that this wall is of a sufficient dimension that it can provide more than three or more spans. So the material which we are going to use is a ply form. This has been given in the example. Okay, that is in the statement of the we are using a ply form. Okay, so what ply form we are using? About 19 millimeter thick ply form over here. Material is 3 by 4 inch thick or 19 millimeter thick class 1 ply form, and its properties from table 4 we can see. So for the design purposes, we will take about 12-inch wide strip, or in the meter units, we will take about 1 meter wide strip. So we will take a 1 meter wide strip. So 600, that is 28.7 kilonewton per square meter will be multiplied by 1 meter. So the linear load will be 28.7 kilonewton per meter. So this will be used in the calculations for the conditions for bending, shear, and deflections. Okay, so here now we can use this. L is equal to 3.16 FBKS over W. So this will be the equation that we will get from table 5. Okay, let's go back to this. So let me see what was that. Remember just that what was the equation? Equation was 3.16 FB. So where is that equation? 3.16. Yeah, this is table 5A. Yeah. So this is the equation which we are using. Here you can see that this is the plywood, right? Plywood. So for plywood, for 3 or more spans, we are using this equation 3.16 FP K times S over W. Okay. Okay. So let's go back over here. So this is the equation 3.16 FBK. So FB is 326 into 10 to the power 3. So FB has for the plywood has been given in the table. So for the plywood, it says that use ply form section properties and allowable stresses from table 6. Okay, so we have to look at the table 6. Table 6. So this is the, so it was ply form class 1, and its thickness has been given. So the thickness which we are using is about 3 by 4 inch, 19.1. So therefore we will use these properties. Its approximate weight is this, and EI value is this. So FB value is this. So it is 326 into 10 to the power 3. Okay, 326 into 10 to the power 3. And that is the allowable stress in bending. Allowable stress in bending. And its other section properties, okay, also. So this is the face grain across the support, that is the, and then it is the parallel to. So this is, I think we will take in the parallel to this across the support. We will use this face grain. So it is 326 value which we will use from here. Yeah. Okay, here 326 divided by the weight, which is divided by the design load, which is 28.7. So FBKS over W. Okay, FBK. So KS is just one quantity. K and S are not two numbers. KS is one quantity. So it's 326 into 10 raised to power 6. Here we can see that. Let me go back to this table 6. Yeah. Which is over here, FBKS. So yeah, so here FBKS is 326. Okay, FBKS. So this whole quantity has been given over here. So therefore 326 into 10 to the power 3 we have used to. So we don't have to consider F, B, K, and S separately. So the product of this has been already given to us. So that has been done over here. So with this, then we can determine that the span required is 337 millimeter. For the shear properties, then we will use the equation for shear, which is 1.67 Fs LB over O over W. Okay, so Fs LB over W, so that we will determine from the table. So therefore, let's find where this equation has come from. So we will go to table 5A, table 5A. Yeah, for the plywood over here, in the case of shear, and then 1.6 Fs LB over Q and then over W. So these are the quantities. So this quantity we can find from the table 6. Yeah, this is given over here. Then what was that value? This value was 7.55. 7.55 into 10 to the power 3. So here I can see that, yeah, 7.55 into 10 to the power 3, and then these values are already here. 2 times D. D is the thickness of the slab, thickness of the sheet. So remember that in the case of beams, we also use this thickness, about 19 millimeter thickness. Okay, about 19 millimeter thickness we have used, but over there the nominal thickness of the sheath was provided, which was 25 inch. So for the nominal thickness, the thickness in terms of D, the value of D was also 19 millimeter. But here 19 millimeter has been directly given to us. So there is slight difference between this and the other example. So by this, I think it should not be 0.19. It should be 2 by 19. So we are using the in the 19 in millimeter terms. So that's why it is 38 millimeters. So 439 plus 38, that is 477 millimeters. So for the shear, the span length required is 477 millimeters. And now, lastly, for the deflection. So for the deflection, we have used this equation 73.8 over 1000. So let's go back, and then it's EI value, and so let's go back to 5A. For the deflection, we will look at delta L over 360, because that was the condition. And for the case of deflection, there is no the distinction between the plywood and the wood. Okay, so there is the same equation. Okay, it is the same equation that will be used, 73.8 EI over W. And what is EI? EI is given here, right? 2810. 2810. So let's go back over here. Uh, 2810 into 10 to the power 9. Yes, it was 10 to the power 9 also. 10 to the power 9. Okay. And then remember that use the units consistently, okay, in a consistent manner. So in these formulas, the length units are given in terms of the millimeters. Okay. So EI, and then where is that? Oh, sorry. Yeah. Yeah, this is the example, and then this is EI 2810 and over 28.7 power 1 by 3. So it is 340 millimeters. So we have got three values. Bending is 337 millimeters, deflection is 340 millimeters. So this means that both bending and deflection almost govern, but bending slightly more. So the maximum span length in this case, it will be about 337 millimeters. So about, so this, which is equal to about 13.2 inches. So in 12 inch is a rather more common figure, 1 feet. So therefore 304 millimeter stud spacing will be used. 304 millimeter stud spacing will be used. So in this way, we have determined the stud spacing of 304 millimeter. So in the same manner, then we will go for the wale spacing. So remember that wale is the same as stringers in the case of beams. So for the wale spacing, when there are 3 or more spans. So since the stud spacing is about 304 millimeter. Okay, now remember that one thing before going over here. Here we have used this pressure value of 28.7 kilonewton per square meter. So in the case of the wall, this pressure value is on the both sides, on this sides or on the left side as well. Okay, so the same value of the pressure we will be using. So that means same types of elements we will be providing on the both sides. Okay, if the spacing on this is chosen as 12 inches, so spacing on that side will be also chosen as 12 inches. But in the case of the slab, we only have to provide the elements on the one side, because that is the vertical space which will be used. Okay, so the next is the, we are here. So select the wale spacing, which is 3 or more spans. So in the same way, first we will determine the load. So in the case of, in the previous step, we determined that the load was 28.7 kilonewton per meter. But this now 28.7 kilonewton per meter load will be used in a space of 0.3 millimeter. That is 28.7 kilonewton per meter. But we are now having a spacing of about 304 millimeters. So therefore, for a 384 millimeter, this load will be only 28.7 kilonewton per meter. Because 28.7 kilonewton is load for 1 meter, but for 0.304 millimeter or 0.304 meter, so the load will be 28.7 multiplied by 0.304 meter. So it will be 8.7 kilonewton per meter. Okay, so 8.7 kilonewton per meter will be the value which we will use over here. So again, first we will calculate the span for the bending. So we will use this equation. So okay, so I will not go back to that table. Now I think you can easily determined. So in this case, remember that in this case, you will not look for the plywood section. You will, in this case, you will look for the beam section, okay? So we will use this equation for the bending, FBS over here. Whereas the value of FB is given here in the 12,480 kilopascal. 12,480 kilopascal. Where is this? Up here. Yeah, 12,480 kilopascal. And the value of S that we will determine from table, okay? Because we are using which section? We are using a 50 by 100 millimeter or 2 by 4 section. So the value of S used is 0.5019 to 10 to the power 5. So we will go back to this table 7. So in table 7, we have which section? 50 by 100. 50 by 100 is 2 by 4. Yeah, 2 by 4 section. So this 2 by 4 section, we have for this 2 by 4 section, we have 0.5019 into 10 to the power 5. Okay, this is the value of the section modulus. And the value of I is 2.231 into 10 to the power 6. So 0.509, and then this is the value of the load which we calculated before. So here we got the value of 849 millimeter. And for the shear, we got a value of 535 millimeters. So in this case, I think the shear is actually controlling it. So we will use this equation. So you can find this appropriate equation over here. And remember that the value of D over here is 88.9. It is not 90 millimeter because now we are using a 50 by 100 millimeter section. That is a nominal section. For this, the value given from the tables is 88.9 millimeter. Okay. And the value of FV, which is 3.387. No, the value of FV, which is 827, is given here. And the value of A, that we can see from table 7, okay, 3.387, okay, into 10 to the power 3. So let's see. Table 7 here. 2 by 4. Yeah, the area 2 by 4 is 3.387, right? Into 10 to the power 3. So into 10 to the power 3, and then divided by 1000 is from the formula. W is we already calculated, and then 2. So it is 535 millimeter. And now for the deflection, it is the same equation as before, which was for the plywood as well. And the value of E is 11.7 into 10 to the power 6. And the value of I will be from the table, and then it will be 1064. So in this case, the shear stress governs. Okay, the shear governs. So the shear gives the minimum span. It is about 535 millimeters. So a maximum span, that is the wale spacing, is about in this case 535 millimeter, which is about 22.36 inch. So for 22.36 inch, it has been recommended that we use a 16-inch modular size. 22.3 inch less, maybe, I think they could even use 18 inch as well, because 18 inch is 1.5 feet. But anyway, they have used it a more conservative value of 16 inch. Okay, about 406 millimeter. Okay, so this is a more conservative value which has been used. So that is to remain on the more safer side. Okay, next we will select the tie spacing. That is the third, which is the third element. 3 or more spans, double whales, and based on a whale spacing of about 406 millimeter. So now we have previously 8.7 kilonewton per square meter per meter, but now we are using only 406 uh, 406 millimeter spacing, and that is being used in a 304 millimeter. So therefore, it will be 11.6 kilonewton per meter. Okay, kilonewton per meter over here. So the load for the tie spacing will be 11.6 kilonewton per meter. So in the same lines, we calculate the length 1039 millimeter for the bending, for the shear 714 millimeter, and then for the deflection it is 1218 millimeters. So in this case, again, the shear cones maximum span is 27.9 millimeter inch or 714 millimeter. So we will select about 24 inch or about 610 millimeter tie spacing for a modular value. And then the next step is to check the tie load. So in this case, the whale spacing, the tie load will be equal to whale spacing, okay, multiplied by the tide spacing, multiplied by the P, that is the capacity of the tie. So in this case, it comes out to be 7.11 kilonewton, which is less than the capacity of the tie. And then another check is to check the bearing. Okay. So check the bearing. So there will be two interfaces. Studs will be lying on, will be supporting on the whales. So on those, in that contact area. So we check that normal stresses in those areas, and then it comes out to be fine. Okay. And then there is another one check in. This is the additional check. This check is not applicable in the case of the slabs. So this check is only for the walls and the column foundations, column formworks. So tie wedges on the wheels. So tie load is equal to was determined over here, and in this case it was also found to be appropriate. Okay, 2462 kilopascal is less than 3340 kilopascal. So therefore, we design in this case, in the design element, you calculated the spaces for all the three elements, and then you performed two additional checks. And also, in addition, there is another check which was for the checking of the tie load. So all the elements have to be designed properly to present the to apply the or to use the design in the practice. So therefore, the final design in this case is equal to the sheathing is the sheathing used is 1.2 by 2.4 meter sheet, 19 millimeter thick class 1 ply foam placed with the long axis horizontal. Long axis horizontal. So, so the studs are 50 by 100 millimeter at about 12 inch or 304 millimeter center to center. The whales, which are same as the stringers in the case of beams, in the case of the slabs, they are double stringers, 2 by 4, that is 50 by 100 millimeter at 406 millimeter on centers. And the ties are 610 millimeter of center. So so at the end we have just summarized our finding over here. So these findings were calculated in the case of this design example, and then later on their appropriateness will be checked by also finding the bearing stresses. Okay. So again, I think in this case, you can see that in this in the case of this plan view, so we have this concrete wall. Concrete walls are being supported on both sides by the sheets. Sheets are supported by these vertical studs, and then these vertical studs are supported by these wales. So wales, in this case, if we take this section over like this over here, so then in the section view, the wales will be shown like this on this section, and those wales are then connected by the ties, and then those connected ties are being used are wedges. These wedges are used between the ties and the wales to provide them appropriate tightness at this joint in the support. So in this way, I think maybe you have to go through this example 1 or 2 times to fully comprehend it. Okay, so example 1 and example 2 are both on the same pattern. Okay. So maybe you can go through it one more time, and then if you have any questions, then maybe you can always ask to inquire about it. So remember that the pattern for these examples is that, first of all, example 2, or it was same in example 1, the same pattern. The description of the problem has been given. Okay, the allowable stresses, the section sizes have been given, and the appropriate conditions. So for example, in the case of the this wall and column form design, the temperature condition and the type of cement and the unit weight of concrete and the pouring rate are important over here, because if the pouring rate is more stresses will be produced more stresses will be applied on the walls. So the calculations will differ, and the formulas will also differ. So therefore, all those details have been provided over here. So after the provision of those details and the allowable stresses, our purpose is to first of all find the design load, use that design load to design the element, to determine the design element, which is in this case, we have fixed it to find the spacings of those elements. So once we find the spacings of all those elements, we will perform the checks, such as the bearing stresses check, such as the stud on wales check, etc. Checking of the tie load, etc. So if all those checks are met, then our design is appropriate, and then we can recommend that design. If one of those tests are not meeting, then maybe we'll have to revise our design. Okay. So in this way, these two design examples work. Okay. Okay, so I think today I just wanted to explain only this aspect. Then in the next lecture on the week, so we will cover the other 2 parts. The remaining part, which is about the design of the lateral bracing. So up to now, remember that up to now we have only covered the for the case of wall, we have covered only the internal supports. So, but these wall supports have to be also laterally supported by the bracing as well. In the case of the slabs, these lateral supports are not required because those shores will be supported on the ground, and then we assume that the ground is providing us adequate support. But in the case of the walls in the horizontal direction, we need to provide some supports. So those horizontal direction supports will have to be transferred on some other secure horizontal support, or those horizontal direction supports may be transferred to the ground so that we can provide the adequate support. So the bracing system is also one of the element in the wall and column design. So these bracing systems have to be also designed. So those bracing systems, I think we will cover in the next week on Tuesday. So I think now I think maybe you can just go through these example 1 and example 2, because we are covering it right at the end of this course. So there is less time to digest these concepts, but therefore it is recommended that you go through these example 1 and example 2 thoroughly, and then so that you will be better prepared for them in the exam. So assignment 3 solution, I will upload it soon, and later on for assignment 4 as well, after its deadline. Okay. So do you have any questions? Do you have any questions? Okay, so that's all for today. Then I shall see you on next Tuesday, and then we will complete this topic. Okay. Bye-bye.